The next thing we'll look at now is what if we have a current loop, but we'd like to find the magnetic field away from the center. So in our picture here, what is the magnetic field due to a current loop at the point P shown somewhere on axis of the ring? Let's deal with the direction first for our magnetic field.
Okay, now what if I have a loop of current, so something that looks like this. I'm going to say that my current is coming around in this direction, and I want to find the magnetic field somewhere off axis. So let's say my pen is the axis. What if I wanted to find the magnetic field out here? Say right here. We'll have to find the direction and the magnitude. The magnitude we'll get from the equation. The direction we'll have to use our right-hand rule, and we're going to have to think about symmetry. So the red pen for right now is my axis. I want to replace it by just a little stack of corks because I can put in elements of magnetic field. Okay, so I want to ask about symmetry. What cancels? What components cancel? So let's say I pick a little ds right here, and I ask, what magnetic field does this little ds make? So now my ds vector goes with my thumb, that points straight up. My r vector is from my ds to my point, the top of my cork. So ds cross r gives a magnetic field that points up and right. And I encourage you to get a roll of tape and try this yourself. So the magnetic field right here, due to this little bit of the wire, points up and right. I'm sticking a toothpick to try and show that. Okay, to ask about cancellation, I did a piece on this side. I'm also going to do a piece on this side. Over here on this side, my ds goes down. Whoops, it knocked over my axis. My ds goes down, that's my thumb. My r goes up this way, and my magnetic field is perpendicular to both. That magnetic field goes up and left. So, due to the little bit of wire over here, the magnetic field it makes is up and to the left. So I hope you can see that the left and right parts cancel and the up parts don't cancel. Okay, so that sort of takes care of the right and left sides of the loop. How about the top and bottom? So up here, my current is going to the right. My R hat is towards my top of my cork. My magnetic field is out of the page towards me and up towards the top of this sheet paper. So that magnetic field points this way. Okay, now let's get the mirror image down here. Down here, the ds points to the right. My r hat points towards the top of my cork. And my B points up out of the page and down towards the bottom here. So you do ds cross r gives me my magnetic field B. So that magnetic field points this way. So I hope that means now that you can see that the up and down components cancel, and we're only left with a component that's on the axis. So we use the symmetry to find the direction of the field.
So real quick, I'm going to try and summarize what we did in the video. So here's my ring. I've got a 3D drawing. Let's say that the current comes around this way. I'm going to draw the magnetic fields that I just talked us through. So I take this little element ds on top. The direction of ds goes with the current. The r hat vector is a vector, unit vector in the direction of r, which is a vector from ds to my point. So there's my direction of r hat. I do my right-hand rule, and I find that my magnetic field due to that little ds points partly in the x direction and partly in the positive y direction. So up and right. So there's the little bit of magnetic field made by that little element of the wire. There's the x, and there's the y. To find cancellation, you always look at the same point on the other side. So I'll go to the bottom part of the loop. This time my ds comes around this way because it has to go with the current direction. My r hat is towards my point P. And doing my right hand rule, I put my thumb with ds, my finger with r hat, and I see that my little bit of magnetic field made by that little bit of ds comes down and right. So negative in the y, positive in the x. There's the y, there's the x. So for every bit of wire on the top half, it has a y component that points up. Every bit of wire on the bottom half, it has a y component that points down. So overall, all the y components cancel. Okay, what about the front and back parts of the loop? What about the z components? So I'll start with a little bit of wire on the z-axis, but in the far back of the loop. My current's in the same direction, so here my ds comes up. My r hat points towards my p, so I do my right-hand rule where my thumb goes with my ds, my index goes with my r hat, and my magnetic field is a little bit in the positive x and a little bit in the negative z. So here I'm trying to draw 3D. It's not actually that easy, but hopefully you watched the video and that explained it with the toothpicks. So there's the x component and there's the z component. To get the cancellation, we'll also look at the little bit of ds over in positive z, so the very front of the loop. The r hat is straight towards point P. We do our right-hand rule, and that little bit of magnetic field comes partly to the right and partly towards us. So in 3D, a little bit like this. So the x component is to the right, z component is forwards. So what we see for the back half of the loop, the z components point backwards. For the front half of the loop, the z components point forwards. That tells us that all the z components cancel. So what's left over is the x direction. None of the x components cancel, so the resultant magnetic field is all in the x direction. Okay, so now we've got the direction of the magnetic field. Next, we'll use the Biot-Savart law and find the magnitude. So let's get going with the Biot-Savart law to find the magnitude. Let's really label our diagram well first. So we've got current I in our loop and show the direction of I. We're going to identify a small part of that loop. And that small part we'll identify with ds. The vector ds has the same direction as our current loop. Our loop has a radius r, so let's label the radius. We're going to try and find the magnetic field at some distance, at some point P, which is a distance x along the x-axis. So we know in our Biot-Savart law we have to use r, where r is the vector from our ds to our point P. So let's draw that vector in. So there's our vector r. R hat is the unit vector that points in that direction. So let's draw in our r hat. And let's see what we can find from here. The magnitude of r is the square root of x squared plus r squared. It's the hypotenuse of a right-angled triangle. We know we're going to be doing vectors, so we're going to need to use an angle. Let's identify an angle. I'll call this angle theta, and I can use sine to find my angle. So sine theta is equal to opposite over hypotenuse, so radius of the loop divided by the distance between ds and our point. And I can fill in what I just wrote down for my r. Okay, so I've got my diagram pretty well labeled. I've got my geometry filled in. So now let's draw in what magnetic field is made by that little element of the wire. If I do my right-hand rule where my thumb is ds, my index finger is r hat, I see that the little bit of magnetic field made by that little element of wire is called dB, and it points partly to the right and partly up. One thing that's important here is that that dB is perpendicular to r. because that's how a right-hand rule works. So there's dB. dB has components because it is a vector. The x component is to the right, and the y component is straight up. This particular bit of ds doesn't make a z component because I picked it where z was equal to 0. And I did that just for ease of drawing, but we already dealt with talking about the z components when we dealt with finding the directions. So we know that the z component total is going to be equal to 0. Let's just deal with that angle a little bit more. So the angle between r and dby is going to be 90 minus theta. And the angle between dby and dB is going to be theta. Okay, I think we're doing pretty well. We want to start finding our magnetic field, so we're going to apply our Biot-Savart law. We know that the y component is the sum of all the contributions to the y components. We know that's going to be equal to 0. And likewise, we know that all the z components sum up to be 0. And that's by symmetry. So that means that our total magnetic field is going to be the x component in the x direction. So next I'm going to find the magnitude of the x component. So my bx is going to be the sum of all the x elements, so the integral of dbx. My x component is opposite my angle, so I have to use sine to find my x component. So sine theta is okay. I know what to fill in for that. What do I fill in for dB? So let's talk about that part next. So my vector dB is equal to mu naught over 4 pi times I times ds cross r hat over r squared. So the magnitude of dB is equal to mu naught over 4 pi times I times the magnitude of ds cross r hat over r squared. The magnitude of ds cross r hat is the magnitude of ds, that's just ds, times the magnitude of r hat, that's just 1, times the sine of the angle between them, and that's 90 degrees. And we covered that in a previous slide. So the magnitude of ds cross r hat is just ds. So that's mu naught times I times ds over 4 times pi times r squared. So I'm going to fill this in for dB, I'm going to fill in what I already had for sine theta, and then I'll finish by solving my integral. Let's carry on now with solving for our x component of magnetic field. So that's the integral of dBx, which is the integral of dB times sine theta. Let's fill in what we have for those terms. So dB is mu naught times I times ds over 4 pi times r squared times sine theta, and sine theta was capital R, radius of the loop, divided by r, which is your distance from your ds to your point P. So that's the integral mu naught I times r over 4 pi r cubed ds. R cubed is going to be, so if r is equal to x squared plus r squared to the 1/2, r cubed is x squared plus r squared to the 3/2. Let's fill that in for our r. So our bx is the integral of mu naught I times r over 4 times pi times x squared plus r squared to the 3/2, and then don't forget the ds. Let's see what we can take out front. Mu naught is a constant. I, the current, is a constant. Capital R, radius of the loop, is a constant. 4 and pi are constants. X, your distance to point P, and the radius of the loop are also constants, so that term comes out front. And we're left with the integral of ds. The integral of ds is what we get when we add up all the little bits of length around the loop. That's just the circumference. So that's going to be equal to 2 times pi times the radius of the loop. Okay, let's fill that bit in. So mu naught I r times 2 pi r over 4 times pi times x squared plus r squared to the 3 over 2. Let's see what cancels. There's a pi on top, pi on the bottom, they cancel. The 2 on top goes into the 4 on the bottom, leaving us with a 2 down there. I think that's all the cancellation we can get. So our x component of magnetic field is mu naught times I times r squared over 2 times x squared plus r squared to the 3 over 2. This gives us the x component of the magnetic field, a distance x along the axis of the loop. For our very last step, we're going to have to write that as a vector. So our very last step is just to write our magnetic field as a vector, which means we include the magnitude, mu naught I r squared over 2 x squared plus r squared to the 3 over 2, put in the direction I hat in the x direction. So something you might notice here is that if you put in your x equals 0, it reduces to the same equation that we had at the center of a current loop. So that's a good thing.